Good evening. Today is our last seminar this semester, and we have a pleasure to have here Takashi Moriya. Takashi did his PhD in the University of Tokyo. Then he was a postdoc in University of Bonn. Works on life on the supernovae and evolution of the massive stars. And after postdoc in Bonn, he back to Japan to National Astronomical Observatory of Japan, and as a postdoc, and after 3 years, he became the assistant professor there. Takashi, floor is yours.
Thank you very much, Marius, and thank you for this opportunity. As was introduced, I'm Takashi Moriya, and I have been working on supernovae, and I'd like to talk about some recent work related to supernovae across cosmic history. So maybe many of you are not familiar with supernovae. So supernovae are kind of transient phenomena on the sky. So if you are observing just sky, then usually you don't see much differences. But sometimes you see some stars suddenly appear, and that's of course there are many different kinds of transient phenomena on the sky, but some of them are supernovae. So this is one example. So on the left side, this is a picture before a supernova, which appeared in 2023. On the right side, yes, one spot appeared after a supernova. So question is, can you spot the supernova? And there's a prize. So this is a Kit Kat from Japan, sake Kit Kat. It contains small amount of alcohol that tastes like sake. So if you can find it, you can raise your hand.
Down below.
Yeah. Congratulations. I can give it to you. Very good. So this supernova, so yeah, this is the new star appeared. So this supernova was found by amateur astronomer in Japan, Itagaki. He's famous supernova hunter, so very famous in the field of supernova. And he immediately spotted, so he knows like every spots on the nearby galaxies. So just at one look, he can immediately identify new star appearing in the nearby galaxies. Anyway, so this kind of phenomena called supernovae. So they become typically after the explosion. You can see how it gets. So they get bright and faint, and there's several different kinds of supernovae showing different kind of luminosity evolution. But typically, they become bright in like 2 weeks, and then some of them stay bright for hundreds of days. Some of them just become faint in a few weeks and so on. But that's kind of typically they become bright in a few weeks and then become faint in several weeks or so. That's the luminosity evolution, and if we take the some spectra of the supernovae, then we also know there's some diversity in spectra. Some of them show hydrogen, some of them show very strong silicon features, some of them show strong helium features, and others doesn't show these silicon, hydrogen, or helium. So these are kind of observed fraction. Many of them are found to have silicon lines, and so these are observed fraction. And some of them have hydrogen, and then 5% helium, and then some less. So, and supernovae are known to be explosion of stars. And we know that there's two different kinds of stars that explode as supernovae. And one is massive stars. So those stars with initial mass around heavier than 8 solar masses, and they are called core-flux supernovae. The other kind of stars that we know explode is white dwarfs, and these are thermonuclear explosion of white dwarfs, so which is close to the Chandrasekhar mass limit in a binary system. So if a white dwarf is just existing just as a single star, then they will just cool down. But if there's another star nearby, this could be another white dwarf or another different non-degenerate star, then mass can accrete to the white dwarf or through the white dwarf with merge, and then it can trigger explosion of white dwarfs. Then we observe them as a so-called type 1a supernova, and these are known to be kind of standardizable. So these type 1a supernovae are used for cosmological purposes. In this talk, I will focus on massive star explosion. So, of course, the question is why we want to study supernovae and why they are important. There's several reasons we want to know details about supernovae. One is supernovae are very major, one of the major production sites of elements. So after the Big Bang, we only have helium, hydrogen and helium, and also some small amount of heavier elements. And then those elements heavier than hydrogen, helium, or lithium, they are different production sites. But these elements up to rubidium, so iron and relatively light, heavy elements are mostly produced by the exploding massive stars, so core-flux supernovae or exploding white dwarfs. Those are type 1a supernovae. So these these elements are produced in this during the supernova explosions. Heavier elements, some of them could be produced by exploding stars, but now we think they may be more contribution from the neutron star merger. So also, once a star explodes, then what happens is they release a huge, not only newly synthesized elements, but that will release a lot of energy to the surroundings. And that will trigger so that will provide energy in the surrounding media, and that will trigger, for example, the star formation of next generation, which will drive the evolution of the universe. So we are interested in how much elements are produced during the explosion, what's the typical energy supernova will release to the surrounding media, and how they propagate to the surroundings, and so on. And of course, after the explosion of massive stars, then there will be a compact object remained. This could be neutron stars. Otherwise, there could be a black hole. Maybe supernova may not be sometimes successful and just forming the black hole. That may be possible. Whatever happens, this massive star, after the explosion, there will be compact remnant left. Of course, that will be these compact objects signature is currently we have a lot of information from gravitational wave observatories, and in order to interpret, for example, mass distribution of black holes or neutron stars that are observed in gravitational waves, we need to understand how massive stars are evolving and how supernova explosions are happening and what kind of mass or what kind of remnants will be left after these phenomena. So I just pointed several big questions, but there's many interesting stuff going on around the supernovae, and this is just what I was saying. But yeah, big question we have is which stars, what kind of mass, which kind of stars, meaning sometimes like which kind of mass stars with which mass will be exploding, how much elements are produced, how much mass and energy will be released, and what kind of neutron stars and black hole will be left after the explosion. So those we want to know by studying supernovae in detail. So what we actually observe is, so after the explosion, as we saw at the beginning, the light luminosity, so how the light will be evolved will be observed. So this is one example of so-called light curve. So what's the time of observation and how bright was that object? So we in this case, I'm showing in two different bands, G band, so in this wavelength range, and then R band in this wavelength range. So depending on the wavelengths, they have a different luminosity evolution, which also contains important information. In this talk, I'm not going to detail about the spectral feature of supernovae, but of course, spectra also tells you about what kind of elements are produced in the explosion and so on. So this is a case of a hydrogen-rich supernova, and so this is what we observe. And then, from theoretical point of view, we can kind of explode the stars, hydrogen-rich star, which is red supergiants, and then see what kind of differences imprinted in this luminosity evolution. So for example, once we observe the light curve, we can get, so for example, if you change the stellar mass, so this is the, again, time after the explosion, and then luminosity in, or brightness in G band. And for example, if you change the mass of the exploding hydrogen-rich star, red supergiants, then these differences in the mass will be, so in these cases, only mass is changed and the other parameters are fixed. So we can see the effect of the mass of the exploding star on this luminosity evolution. So as the color gets towards yellower color, then so in this direction, the mass gets higher. So with higher mass of stars, then you tend to have slightly brighter luminosity, and also this duration of the bright phase. So there's some drop here after some time, but this duration of the large luminosity will be longer for higher mass stars, for example. And then if you change the exposure energy, then so with higher exposure energy, it goes this way. And with higher exposure energy, you get brighter supernova. And also this duration will be shorter. And one of the important property of supernova is after the explosion, a lot of 56 nickel will be produced during this explosion. And this 56 nickel is a radioactive element, and that will decay in to cobalt 56 in about 10 days. And then afterwards, this cobalt 56 will decay to iron 56 in about 100 days. And iron 56 is stable, so it will no longer decay. But because this decay timescale is close to similar to this luminous phase of supernova, so this mass of this radioactive element is also affecting the luminosity evolution quite a lot. So once we change, so this is low mass nickel, and this as it gets brighter, there's more nickel. So especially at the early phase, there's not much effect on the luminosity evolution in the from the nickel 56. But then towards the late phase, you have quite a differences, and especially after this drop, this luminosity evolution is or brightness is quite sensitive to the mass of nickel 56 produced, and this will decay to iron. So in order, so constraining this mass is important to constrain how much iron is produced in each supernovae, for example. So this has a lot of information on nucleosynthesis. And also recently, it turned out, so in the exploding star, we have been thinking there's not much material. So there's a star, and then it will just explode freely. But actually, in recently, it turned out when the supernova explode, especially in the case of core supernova, these massive stars are having a lot of mass loss because it's bright and has mass, a lot of mass that can release. So it turned out often there's dense circumstellar matter surrounding this exploding star. So what this shows is if we change the density of this surrounding material, so this black is less material surrounding, and then the yellow is more material surrounding, and this is showing in the unit of mass loss rate. But higher mass loss rate basically means more mass surrounding the exploding star. And if there's a more denser circumstellar matter, then there will be a strong shock wave between this exploding star and dense circumstellar matter, which converts the kinetic energy of this exploding supernova ejector efficiently to radiation. So if there's a denser circumstellar matter, then there will be a strong effect of this shock wave produced in between the supernova ejector and the circumstellar matter. So as the density gets higher, then you see the effect or brighter luminosity evolution at the beginning. Then afterwards, as the supernova shock wave expands, then the denser part of the circumstellar matter is swept up, so you don't see much effect later on, unless there's an extremely large amount of mass surrounding the ejector. But anyway, this circumstellar matter is known to be affect the early phases of this luminosity evolution of supernova, which turned out to be very important, as we will discuss later as well. So we have like a different properties of exploding star and the explosion properties that will affect the luminosity evolution, and we can make a kind of grid of these models with different combination of different parameters. And then what we can do is we have observed luminosity evolution, and then we can do, for example, MCMC and like make a Bayesian approach to estimate these other possible properties like mass, and of course sometimes extinction is important, energy, and the circumstellar matter properties, and so on. And then what we can do is we can apply, so there's now hundreds of supernova. In this case, I'm showing the hydrogen-rich cases, but there's hundreds of supernovae. We can apply these kind of methods and then see what's the general property of supernovae. So this is one example of this kind of study trying to model this luminosity evolution of hydrogen-rich supernova. And then for each supernova, you get probability distribution functions for the properties, ejector mass, or energy, and so on, and then combine these numbers and see what's the general properties. So this is detailed study of 51 hydrogen-rich supernova. So this is the ejecta mass, estimated ejecta mass distribution. So, so as kind of we expect, there's less. So in terms of, so these hydrogen-rich supernovae are coming from massive stars. And if you think of IMF, initial mass function, then lower mass star should be more dominant. As expected, we see more smaller mass explosions, which is coming from IMF. And then as you get higher mass, you see less probability. And this is explosion energy distribution. So this is 10 to the 51 elves, which probably many of you here, like typical explosion energy of supernova is 10 to the 51 elves. Actually, recent studies show that many supernovae tend to have a relatively lower explosion energy than 10 to the 51 elves, and many, let's say, average explosion energy of core of supernovae may be more like 0.5 or 5 times 10 to the 50 elves, so less than what you have been told in the classes, but that typically we find the explosion energy of around order of 10 to the 50 elves. So this kind of information, so previously 10 to the 51 elves were found from, for example, supernova 1987A, the famous supernova in the Large Magellanic Cloud. That was around 10 to the 51 elves. And many supernovae studied in the earlier time had around 10 to the 51 elves. So that's kind of discussed to be a typical energy, but for the corpus of supernovae, slightly less energy seems to be more typical explosion energy. Of course, type 1A supernovae, which is different kind, they have a typical explosion energy of around 10 to the 51. But if we focus on corpus of supernovae, their typical explosion energy is slightly lower. So among these, so these are like explosion properties, but what has been very interesting for us was, so typically, if we observe a supernova just after the explosion, so this is showing the time and the brightness in optical band. And what we, in the last decade or so, there's like a lot of transient survey monitoring very like large field of sky very frequently. So we have been having many cases, there's non-detection, and then suddenly you get supernova, and then it gets like bright supernova light cloud from the shortly after the explosion. And theoretically, we have been modeling this hydrogen-rich supernova for a long time. And the typical prediction was it takes about 10-20 days or so optical light to reach the maximum luminosity. So that is coming from the kind of cooling time scale of this exploding star. So at the beginning, the exploding star is heated by the shock wave, and it has tens of thousands of kelvins. So it's quite hot, so it's quite faint in optical band. But as they expand, then it cools down, and in the end, the temperature become around 6,000 Kelvin or so, where the luminosity, most of the luminosity goes to optical regime. So this time scale for the luminosity to rise in the optical band were thought to be related to this cooling time scale, and then in the optical, it should be around 20 days or so. But what has been observed in last decade was it turned out to this many of these type 2 supernova or hydrogen-rich supernova have a much quicker rise than it has been predicted. So that was a big mystery, but this was kind of these differences were currently interpreted as effect of this dense circumstellar matter. So if there's a dense circumstellar matter, then you can have a shock wave that can provide extra energy to explain this early phase luminosity. And And also, this is we are discussing the luminosity evolution, but if we take spectra, then we also we are starting to find the clear signature of the circumstellar matter interaction in these early phases. So now we found that so previously, like 15 years ago or so, we are thinking that supernova explosion is happening in a relatively clean environment without much circumstellar matter. But now we found most of the supernova are showing the effect of this circumstellar matter interaction, and that is making this luminosity evolution much quicker than we expected before. So based on this kind of luminosity evolution, again, we can estimate what kind of mass should be surrounding and what should be the mass loss rate of these exploding stars. So this is based on this kind of fitting. We estimated the mass loss rate of these stars shortly before the explosion. So this is kind of distribution we found by numerically modeling this early luminosity evolution in hydrogen-rich supernova. And what we found is this distribution. So most of the stars, exploding stars, are having the mass loss rate higher than 10 to the minus 4 solar mass per year. And these hydrogen-rich stars, so these are explosion of red supergiant. And then we can also measure the mass loss rate of red supergiant in the nearby universe. And then what we typically expect, or what we typically observe in the red supergiant in the Milky Way or LMC is the typical mass loss rate we observe is less than 10 to the minus 5 solar mass per year. Of course, that was the reason why we were not thinking this circumstellar matter should not affect much supernova property because the mass loss rate is too low. But actually, it turned out the mass loss rate of red supergiant just before the explosion is somehow the mass loss rate is enhanced shortly before the explosion. Shortly means about like decades or centuries before the explosion. This red supergiant should be experiencing higher mass loss rate than before. So that's kind of what we are starting to find by detailed observation and modeling of the supernovae in the last decade or so. And this is very kind of confusing, and we don't know exactly why this is happening. This is because so we often write this kind of onion-like structure of massive stars about to explode. So we are talking about hydrogen-rich stars. But so this central region is very nearly at the center, and so this explosion is triggered by the collapse of this central region, which is like within 10 to the 4 kilometer. But this red supergiants, the mass loss is happening at the surface of this star, which is around 10 to the 8 kilometer. So so explosion is triggered at the center, but mass loss is happening at the surface. So naively, if we think that stellar evolution is mostly dominated by the thermal timescales or nuclear timescale, nothing will. This thermal or nuclear timescale is much shorter, so much longer than the timescale of collapse, which happens in the final stages of the stellar evolution. It just happens like in like 100 years or 10 years, it will collapse. The central region will evolve to collapse. But at the same time, somehow we are starting to find that this surface is somehow start to lose strong mass loss centuries or decades before the explosion. So we have not been thinking these central crops will affect the surface property, but we are starting to find somehow the central crops final stage of evolution is affecting the surface of this exploding star. We still don't have idea how this is happening. Of course, dynamical timescale is much shorter than very short, so like days or so. So if there's some way dynamical effect that can propagate the central evolution towards the surface that can trigger the mass ejection at the surface, then that may explain this strong mass loss happening just before the explosion. But we don't know exactly what's the cause of this phenomena. So that's this big mystery we are starting to find, but we still don't know what's going on here. So far I have been talking about the like general property of supernovae, which were estimated by kind of detailed assessment of the supernova, which observed quite very well. So those are kind of observed in a nearby universe. So this is kind of redshift evolution of hydrogen-rich supernova that were found in until very well observed type 2 hydrogen-rich supernova by 2020. So most of the properties I showed, like explosion properties, mass, and the circumstellar matter properties, are basically obtained by doing research in the relatively nearby type exploding stars. So, but we are suddenly finding a lot of high-redshift supernovae through James Webb Space Telescope, and this is quite new. And so this, how this happened is, so this is there's a survey called JWST Advanced Deep Extragalactic Survey, JACE. And they were basically, their interest is high-redshift galaxies. So they were not interested in supernova at all. So they just wanted to have a high-redshift galaxies. So they asked to observe a certain field on the sky as deep as possible. And they asked so many times, it turned out it is technically unfeasible to observe this field, the field which is in black region. They wanted to observe this field very deeply, but they couldn't observe at one time. So they are forced to separate the observation 1 year apart. So they just by chance took this the image, very deep image of this region 1 year apart. And then what we did is we just subtracted these two images. And then all the dots shown here is the supernova candidate we found by subtracting these two images 1 year apart. And then afterwards, there's many interesting supernova candidates. So we asked for the extra time to follow interesting candidates and other like scales like the observation JWST did later on. So each observation went to about 30 magnitude, which is crazy. But suddenly, all of the sudden, we get this very deep images having time domain information in which we can search for supernovae. And indeed, we found very interesting supernovae. And so we have been, as I showed, before this JWST observation, most of the supernovae, especially core supernovae, were redshift 0.2. But after this JWST observation, we suddenly found this hydrogen-rich supernova at redshift of almost 4. Type 1 supernovae, before this survey, the highest redshift type 1 supernova was around redshift of 2 or slightly below. We suddenly found type 1 supernova. So these are, we also took spectra. So we know these are really supernova at redshift of almost 3, and another kind of supernova which are typically associated with gamma ray bursts are also found at the redshift of almost 3. So we are suddenly having this high redshift supernova information from the JWST. And of course, one question everybody may ask about this high redshift type 1a supernova is how if this can be used for to estimate the cosmological properties. So this is what we did. So this is Hubble diagram, and what we did is we didn't use this high redshift type 1a supernova to fit this cosmological parameters, but just extrapolated this fit obtained from the more closer type 1a supernovae. And if you assume lambda CBDM and then extrapolate this fit, then this type 1a supernova redshift of almost 3 is basically on this line. So that means that this is interesting in several ways. One is we are finding type 1a supernova at redshift of 3. That itself is quite interesting. Some people predict type 1a supernova rate should drop beyond the redshift of 2, which is not what we are not observing. So there's some type 1a supernova at redshift of 3. That's already interesting. And also this seems to be following this lambda CDM. So that means at even redshift of 3, type 1 supernova may be still working as a standard candle, which is not obvious. But this kind of information we are starting to get from this high redshift type 1 supernova. And we have been talking about the hydrogen-rich supernovae. So we found like 6 hydrogen-rich supernova at redshift beyond 0.5, so which is much higher than the hydrogen-rich supernova we have been working before. So this one is redshift at 3.6. This is 2.6, 2.3. So we are suddenly getting this high redshift type 2 supernova, hydrogen-rich supernova. So what we did is, again, we did the same exercise as we did in the nearby supernova and try to model this luminosity evolution and try to get the properties of high redshift supernovae and see if there's any differences in the supernova properties in the local universe and the high redshift. So as I said, there's still only 6 hydrogen-rich supernova we are sure they are hydrogen-rich supernova explosion of red supergiants. So we can only discuss their properties based on the 6 supernovae, but these are kind of estimated properties we got from this observation. So mass is quite difficult to constrain because mass, as we were seeing, mass, in order to estimate the mass property, we need to have like a duration of this luminosity. But because these supernova are at extremely high redshift, even if we keep observing 1 or 2 years, in the rest frame, it's only like several days or so, tens of days. It's not like hundreds of days. So we need to be very patient to get the entire light curve. But JWST hasn't observed this field long enough to constrain the like duration of this type 2 supernovae. So we still don't know, we couldn't get much good constraint on the mass itself. But the explosion energy is mostly affecting this luminosity. So that we have a relatively good idea what's the energy of these explosions. So these explosion energy we can relatively constrain well. So this is shown in the units of the 10 to the 51 L's. And as we were seeing at the beginning, typical explosion energy of this hydrogen-rich supernovae in the nearby universe is about 0.5 10 to the 51 L's. But what we found is many of them have, we only still have a 6, but many of them have much higher explosion energy than what we typically get in the local universe. And many of them have like 3 times 10 to the 51 Ls, which hasn't been observed in the local universe almost at all. So it seems we may be getting a relatively larger fraction of large explosion energy explosions in the high redshift universe. So this is what I was saying. So many supernovae. So in the local universe, we have several like 10 to the 51 L, slightly higher ones, but not like 3 times 10 to the 51 Ls. But among 6 samples, we already have like 2 of them. So it looks relatively high. But as I have been saying, this is still very small number statistics. So we need to be more patient and get more supernovae to make firm conclusions. But it seems this is if we may be seeing more higher exposure energy in the higher redshift universe. And that could be an effect of metallicity, for example. At higher redshift, the average metallicity of the universe is lower. So we may be seeing that explosion energy at lower metallicity environment maybe tend to be higher than higher metallicity stars. And of course, brighter, so higher explosion energy makes the supernova brighter, and then there could be a selection effect that we may be observing brighter ones easier. So that's why maybe we are picking up higher explosion energy. But so this is showing that this figure is showing the luminosity of very typical explosion so very standard explosion of the supernova, how the brightness become at the peak become how bright the peak will be as a function of redshift. So, but each JWST observation is reaching around 30 magnitude. So typical supernova, if they are exploding, then we should be observing the typical supernovae, hydrogen-rich supernovae, up to redshift of 5 or so. We can easily, if they explode at redshift 4 or so, we can easily find supernova with standard explosion energy. So because JWST observation is very deep, we think we are not strongly biased towards the brighter explosion, brighter, more energetic explosion. So if there are more standard supernova, we should be observing them as well. That's what we think. But of course, again, we are still talking about 6 samples, so we need to get more data and see if this is true or not. And also, in order to constrain these circumstantial properties, we need to have a luminosity evolution just after the explosion. So, which is not often the case in our sample now. In some cases, we found this supernova called relatively early. So we could constrain the mass loss rate of this progenitor. And in such cases, we found this circumstantial property or mass loss rate should be relatively high, as we observe in the local universe. So this kind of mysterious mass loss happening shortly before the explosion of massive stars seems to be also happening at high redshift. So this mass loss may not be kind of related to metallicity. So somehow this connection between central cracks and the surface mass loss is happening in the early universe as well. Yeah, so that's what I just said. This may be metallicity independent processes are playing a role in making this dense circumstantial matter. So that's what I have introduced. So I have introduced supernova important phenomena in the universe to study, and we have been studying the local supernova properties quite well, and we are starting to have an idea of general properties of supernova in the nearby universe. And then at the same time, we are suddenly starting to get high redshift supernovae from JWST, and through that the high redshift JWST supernova, we are starting to have an idea of the supernova properties at high redshift, which may be slightly different from, well, in the local, maybe different from the supernova properties in the local universe, but we still have only small amount of samples, so this needs to be this kind of survey needs to be continued, and actually JWST is assigning time to keep monitoring this field, so we are getting more high redshift supernovae and see what would be the differences in the supernova properties in the local universe and high redshift universe. That's it. Thank you very much.
Okay, time for question. Okay, Dorota, please.
Thank you. I have a question about this potential metallicity dependence. You said that higher explosion energies are in the higher redshift. So, and you said that might be an effect of metallicity.
Yeah.
Or selection effect. So, is it difficult to measure the metallicities of these very different galaxies?
Yeah. So we can.
In order to verify this.
Oh yeah. So in some cases we have host galaxies, and then we can estimate. Sometimes even we have the spectra of these host galaxies, and I'm not showing the metallicity of all single object, but typically this host galaxy has the metallicity of about 10% of solar metallicity. So we are basically probing the explosion properties of stars in about 10% of solar metallicity in this sample.
Okay, Martin, you.
I was wanted to ask about 1A supernova.
Yep.
There are 6 hydrogen, and how many?
Type 1A. So with spectroscopic confirmation, we have now 3. And of course, it's difficult to get spectra. So if we just type 1 supernova, you can also get a good idea by just fitting the light curves, photometry. Then I think I forgot, there's tens of type 1 supernova candidates at high redshift.
Yes,
3 spectroscopically confirmed. Yeah.
Thank you. Without spectroscopy, you have no certain redshift.
Yeah.
Okay, more question. Please.
So what do you infer about the rates of the supernova effect?
Yes, so that's an interesting question as well. So we are currently working on the rates, and Cockcroft supernova rates are kind of currently estimated up to redshift of 1.5-ish, which is around the peak of star formation history, cosmic star formation history. And big question is if supernova rate follows, and after above redshift of 2, the cosmic star formation history will be dropping. And the big question is if the Cockcroft supernova rate follows that or deviates. And with very rough estimate we have so far, it seems this supernova rate above redshift of 2 is following the cosmic star formation rate history. So starting to drop following the cosmic star formation history. So that's what we are starting to find. So for example, some people predict if the IMF gets top heavier at higher redshift, then the Cockcroft supernova rates should be higher than what you expect from the cosmic star formation history because you have more massive stars, which is we are not observing based on the very initial rough estimate of the rates. So we are seeing the supernova rate is following the cosmic star formation history.
Okay, Radek.
You twice showed to the histograms of the mass loss rate, which is what's the source of that? Yeah, that one. Is it prediction or it's measured somehow?
So this distribution is estimated based on kind of this kind of fitting the light curve.
From analysis of supernova.
Exactly. Yes.
So
so just to add, so this circumstantial property is very sensitive to this early phase luminosity evolution. So if we can observe supernova very early on, then that will give you a constraint on this circumstantial property.
okay, I don't see the question from the room. We have the question from online participant. Tomek, could you unmute you and ask the question?
Hi, can you hear me?
Yes.
Yes.
Great. Takashi, very nice talk. Thank you for summarizing this in a very clear way. You showed in one of the tables that you're getting those supernovae with mass loss rates of 10 power minus 3. And if they were supergiants, I would expect a lot of dust in such a high mass loss rate because the objects, the red giant or supergiants in our local universe, if they have such a high mass loss rate, they're super dusty. And then there is some local extinction. But in your tables, you write EB minus B is 0. Is that something else that I am assuming?
So this extinction is estimated based on the supernova luminosity evolution, supernova color. So before the explosion, there could be dust surrounding this exploding star. But when the supernova explodes, there's strong UV photons, basically destroying all the dust surrounding. So we don't see the effect of this dust formed in this circumstellar matter in the supernova property because supernova itself will destroy all the dust. So this is basically estimated from the supernova itself. So this is not the local extinction, but the more global extinction of the site the supernova is happening. And actually, if I don't have a figure here, but if we look into this explosion site of this supernova with high extinction in the galaxy image of the host galaxy, then they are kind of in the region where like close to the center of very dusty galaxy and so on. So it's this supernova itself exploded in a very dusty environment, but this is not the local dust formed by the exploding star itself.
Okay, understood. But if you have a red supergiant that can lose mass for hundreds of years with this mass loss rate, you don't get the dust immediately destroyed, right? If you observed early on, you should be able to.
Before the explosion, if we can observe them before the explosion, yes.
Or just at the very beginning of the
extinction. That's also true. So in one case, like needs to be, it needs to be caught almost exactly at the time of explosion. Then you may see the luminosity evolution where dust is kind of destroying. And then, so that can be actually seen if you can observe supernova just after the explosion. And in one case, such kind of luminosity evolution or color evolution is suggested to be observed in the case, actually, the supernova I showed at the beginning in 2023 IXF. That was caught just after the explosion. And then they observed in the near infrared as well, and then they find a peculiar color evolution that can be explained by ongoing dust destruction happening in the exploding star.
All right, thank you very much.
Thank you.
Thank you, Tomek, and congratulations the James Webb Times Awards.
Thanks.
Congratulations. Another kick cut.
Okay, another. Do you have any more question? Okay. This is our last seminar this semester. Let's thank the Takashi again.
Thank you very much.
Very good.
Thank you.
Very nice. Very nice. Very timely. Okay.